energy and position of electrons are complementary. So we can describe the kinetic energy of an electron as 1/2 mv squared, the mass times the velocity squared. If we know a given energy for the electron, then the best we can do to describe its position is to say it's in this region, and we call that an orbital. It's a probability distribution. Many of the properties of atoms are related to the energies of the electrons. And so, in general, we're much more interested in the energies of the electrons than in their actual positions, because they're moving anyway. So Schrodinger, the same guy with the cat experiment, and somebody asked me a question after class. I just want to be clear. Schrodinger's cat was a thought experiment. It did not involve a real cat. Okay, no cats were harmed. Why did he choose a cat? I don't know. Right? So that was just in your head. But Schrodinger has an equation that allows us to calculate the probability of finding an electron that has a particular amount of energy at a particular location in an atom. And this is the overall expression of Schrodinger's equation. These are wave functions. I can't remember. I should have looked it up because I didn't remember this last night either. Does anybody know what Greek letter that is?
Psi.
Psi?
Psi, yeah.
Okay. So psi here represents a wave function. And those wave functions describe the wave-like nature of the electrons. So I do not completely understand what electrons are doing. You are not going to completely understand what electrons are doing. I don't know that anyone really does. There's some people that are much further along than I am. But honestly, I just don't care that much, right? I need to know as much as I need to know to understand the rest of chemistry, and that's the goal for you guys, is just to get you to where we need to be. So I think it's helpful to think of an electron as being like a standing wave. And so that standing wave occupies some space. So you could take that wave function squared and plot that, and that could represent the orbital, that's space. So the energies have to be quantized. The energies of the electrons have to be quantized. And so the calculations are quantized by adding 3 integer terms into the wave function so that we end up with quantized energy for the electrons. So these are called quantum numbers. The first one is the principal quantum number, and that's signified by the letter N. And then we have the angular momentum quantum number and the magnetic quantum number. There's a fourth one that's the spin quantum number, but that one is not an integer. I want you to, play along here and try to see the relationship between the possible values of these integers. I am not going to ask you what the symbol for the angular momentum quantum number is, because I get the angular momentum and the magnetic one mixed up. We don't really need to know that. But let's talk about what these integers represent. So that first one, N, this is a lot like Bohr's energy levels. So this determines the overall size and energy of an orbital, this place where an electron is likely to be found. The larger that N is, the greater the energy and the larger the orbital size. So if we go back and look at the Bohr model for a minute, it's back here somewhere. There it is. So these orbits that Bohr had are a lot like energy levels. As you get farther from the nucleus, the energy of the electron gets higher and the orbit gets bigger, right? So the principal energy levels are like that. As as n gets bigger, the orbital itself gets bigger, and the energy increases. And that's why I like the Bohr model, because it at least gives us this place to start that's not totally abstract. For hydrogen, we can use that principal quantum number to calculate the energy of the electron. So the energy of the electron in a hydrogen atom is equal to negative 2.18 times 10 to the minus 18th joules times 1 over n squared. And this is coming from the Rydberg equation, right? This 1 over an integer squared. So if n is 1, then 1 over 1 squared is just this number. If n is 3, then it's this number divided by 9. And that corresponds with the lines that we see in the emission spectrum from hydrogen. The energy here is negative because the electron's energy gets lowered by its interaction with the nucleus. So you can kind of think of zero energy as like zero altitude being at sea level. Positive energy would be higher, and we understand that. But as we go from zero and we go down, the negative numbers are getting larger, but we're going down, and so it's lower energy. That one's kind of hard to understand. Another important thing is that as n gets larger, the energy difference between the orbitals gets smaller. So if we think of it as like being the ladder, just because there's not enough space to draw anything else here. As you go up the ladder, the rungs get closer and closer together. So the energy levels for the electrons, as they get higher in energy, they also get closer and closer to each other. So for hydrogen, an electron in the first principal level, there's its energy, and here's for n equals 2, n equals 3, and n equals 4. So they're getting closer to each other.
So anytime we see n equals whatever, it's asking for hydrogen. Is that correct? Only hydrogen?
No. We're talking about hydrogen now because it's easier, but that's the energy level for the electrons, the main energy level. I've got an analogy that'll come up in the next chapter that I think will help. So the next quantum number describes the shape of the orbital. And the values that are possible for this number, L, depend on what n is. So L can be anywhere from 0 to 1 less than n. So if I'm an electron on the 4th level, right, n equals 4, then I have possibilities for L to be 0, 1, 2, or 3. So the value of L, these are numbers, but for historical reasons, we often refer to these with letters, S, P, D, and F. Now, for those of you that took Chem 3A, do you remember hearing about things like 1s2, 2s2, 3s? Yeah, electron configurations. This is the S, P, and D stuff from the electron configurations. The number in front of it, like 1s or 2s, that's the principal quantum number. So if n equals 3, what are the possible values for L? L can be 0 up to n minus 1 integers. So if n equals 3, it can be up to 3 minus 1, which is 2, right? So we could have 0, or 1, or 2. And those would correspond to S, P, and D. The third number is the magnetic quantum number, and this gives us the orientation of space relative to the other orbitals. The values that this can have are from negative L up to plus L, including 0. So if L is equal to 2, then M sub L can be anywhere from negative L would be negative 2, up to positive L, which is 2. So there's negative 2, negative 1, 0, 1, and 2. So there's 5 different values there. This question is dumb because we just talked about this one. What if L equals 1? What are the possible values? We can go from 0 up to n minus 1, which is, wait a minute. Yeah, that was L equals 2. So this one can go from negative L to positive L. So if L is 1, we could have negative 1, 0, or positive 1 are the possible values. So that would be this one. Just trying to see if you're paying attention. Yeah, let's see. The last one is the spin quantum number. This has 2 possible values, plus 1/2 or minus 1/2. And so these indicate the spin of the electron. Electrons are not spinning like tops. Any of you guys play with Beyblades when you were younger? Maybe you still do, it's okay. But Beyblades are little tops and they can spin clockwise, and there's also some launchers in some Beyblades that you can spin counterclockwise, right? There's no other options. It's clockwise or counterclockwise. So the plus 1/2 and the minus 1/2 are like clockwise and counterclockwise. But the electron is not spinning like a top. But we can think of it and be fine. So these are described as up being the plus 1/2 or down being the minus 1/2. So to describe an orbital, we use the principal quantum number and the angular momentum quantum number and the magnetic quantum number. So we're going to use the first 3 quantum numbers, n, l, and m sub l. So if we have this combination where n is equal to 1, l is equal to 0, and m sub l is equal to 0, that's going to describe the 1s orbital. The 1 here is this number 1, n equals 1. Where does s come from with the 0? Well, the possibles are 1, 0, 1, 2, 3, and we call those S, P, D, and F. So when L is 0, we're going to call that S. And there's only one possibility for M sub L. This only can have, doesn't have an orientation relative to anything else. So orbitals that have the same value of n are said to be in the same principal level, and orbitals that have the same values of n and l are said to be in the same sublevel. Okay. So here's at least something visual we can look at. So when n equals 1, there's only one possibility for L. It has to be 0. And so that's an s orbital. And with L being equal to 0, there's only one possibility for m sub L, and that's 0. There's one orbital here. On the second level, which we'll get to my hotel analogy, I'm going to turn this into the Quantum Hotel, a discount resort for electrons in Mrs. K's chemistry land. That'll be coming up next week, I think. So this is like the second floor of the hotel. There's 2 sublevels. Those are like the rooms in the hotel. And in this first room, there's 1 bed, and in the second room, there's 3 beds. Why are there 3 orbitals over here? Because L is equal to 1, so m sub L can be -1, 0, or +1. Over here, m sub L can only be 0, so there can only be 1. Up here, n equals 3. Now we have 3 different sublevels. The s sublevel always has the 1 orbital. The p sublevel has 3. The d sublevel has 5. List the quantum numbers associated with all of the 5d orbitals. How many 5d orbitals exist? I would never ask this on a test. Well, if we're talking about 5d, then what does n equal? 5. Because this number is n. 5d means n. And then, 5 means, whatever. My goodness. And then it says, so this is 5d. So 5 is the energy level, and d tells us about the sublevel. So d means that L is equal to 2. And if L is equal to 2, what are the possible values for m sub L? You can go from -2 up to +2. So the possible quantum numbers would be 5 to -2, 5 to -1, 5 to 0, 5 to 1, and 5 to 2.
You just need to skip this example.
You could think of this as a little bit like an address or an ID number, right? What we're going to see is that each electron has its own set of quantum numbers that describes where it is. I do not expect this to make any sense at this point, honestly. I really don't.
Are we going to have to memorize these, or is there like a way to find them, like derive them?
I am not going to ask you about the values of these other quantum numbers, right? You'll need to know things like there are 5d orbitals and 3p orbitals, but I'm not going to ask you what their quantum numbers are.
Oh, like the constant one.
Okay.
Just go ahead and skip it.
But this is showing us that there are 5 different orbitals that exist in
So
this.
why does it go 5, 2?
-2 and then
And
5,
then
2.
I know I get the ends, like -2, -1, 0, 1, 2. I get that. But why does each set start with 5 and 2?
Because it's on the 5th level and the D sublevel. And D represents 2.
Oh, these. Okay.
So I'm kind of jumping ahead into the hotel analogy. But this is a D sublevel, right? This one's 3 instead of 5. So this is describing the set of numbers for each of these boxes. So in the hotel, you could say, oh, well, this electron's staying on the 5th floor in the D room and it's in bed -2.
So it just changes beds every time, basically.
Yeah.
It keeps it's in the same.
Yeah,
level,
so we're talking
same
about the
level,
electron
same
staying
bed.
in this same room, and the difference at the end is just which bed is it sleeping in.
Got it. It's a whore.
No,
Got it.
we'll find
I
out
can-
later.
I can deal with this. That
No,
makes
we'll
sense.
find out later that they actually sleep head to toe and no funny business goes on.
This makes sense. Okay, I can deal with this.
This
Here,
is
maybe
going
leave
past
that
the-
out of the
This
presentation.
is going past the chem class, guys. That's enough.
Gosh, this is crazy.
It is crazy. There's a question like this on the worksheet, so I want to do this. Each set of quantum numbers is supposed to specify an orbital, but there's a mistake. Replace the mistake, the quantum number that's not allowed, with one that is allowed. So, n can be 1, 2, 3, etc. L can be 0 up to n minus 1. M sub L can be from negative L to positive L.
We still have an A wrong.
Well, all of these has something wrong in them. So, can you have a principal quantum number 3? Sure you can. If n is 3, can L be 3?
No.
No, because L can only go up to 3 minus 1, which is 2. So, this is the one that's wrong. So what number can we put in there that will still work with this m sub L being positive 2? 2. So that's a possibility. Here we've got n is equal to 2, so if that's the case, can L be 1? Yeah. Can m sub L be negative 2?
No.
No. It could be negative 1, 0, or positive 1. So there's 3 possible answers you could choose from here. I'm just going to call that one 0. That would be a possibility. If n is equal to 1, can L be 1? No, because L can only go up to n minus 1. 1 minus 1 is 0. So this could only be 0. And if L is 0, m sub L will be 0. Okay, I want you to get this enough that you can do the worksheet, asking questions, looking at the book, whatever. I would never give this on an exam because it's not that important. Okay. Okay, so now we can explain the emission of light from elements. Each wavelength, each line in that atomic spectrum corresponds to an electron transition between orbitals. If the atom absorbs energy, it goes from a lower energy level to a higher energy level. That excited state is unstable, just like the excited state of humans is unstable. I mean, you think about little kids at a birthday party or something. They're all like, oh, all excited and stuff. But do they stay that way all the time? No, you can't maintain that level of excitement. You crash sometimes. So the electrons can go to an excited state, but then they always come back down to a ground state. So they'll always relax back down. When they come back down, they're going to release a photon of light with energy equal to the difference between the orbitals. So here we're looking at hydrogen, and we've got this one electron, and it absorbs energy and goes up to the 3rd energy level. It's now excited. But it can't stay there. It's going to fall back down. It could fall all the way back down to the 1st level, or it could fall to the 2nd level, and then later it would probably fall to the 1st level. But every time it falls, it's going to emit a photon of light that's equal in energy to the difference. So it could absorb a photon of light with this amount of energy, and then it could release one here when it comes out. So it has to get just the right amount of energy. There are some buses that only accept exact change. I don't know if any buses accept change anymore, but it used to be that, you pay a quarter and get on the bus or whatever. Well, what if you only had a dollar bill? Well, I understand them not making change, right? But if you had too much, they wouldn't let you on either. It had to be exact change only. It's kind of how this is. You have to have just the right amount of energy to go from between those two levels. If you've got a little more, nothing's happening. High energy states are unstable. The electrons will tend to lose electrons and fall back down. And then the lines in the emission spectrum correspond to the difference in energy. For hydrogen, we can predict the lines by calculating the difference in energy between any two states. And there's some questions on the worksheet to have you do this. So the Bohr model and the quantum mechanical model both work for a one-electron system, hydrogen. So this is the energy information for hydrogen. So the change in energy, which would represent the energy of the photon that's being released, is the final energy minus the initial energy. This is the amount of energy that the electron loses by going to a lower level. Well, the energy of an electron is minus 2.18 times 10 to the minus 18th joules times 1 over its principal quantum number squared. So we take this for the final position and we subtract for the initial position. We simplify and we get this little guy here. Now, the signs can get a little confusing here. When the electron is going down, it's losing energy, right? So delta E is going to be negative for the electron, but where's that energy going? That energy becomes a photon of light that's going out. Can a photon have negative energy? Mm-hmm. No. It would have to have like a negative velocity or a negative wavelength. It doesn't work, right? So the change in energy for the atom is opposite in sign to the change in energy for the photon. And we also, this is from earlier, it was shown earlier as E equals hc over lambda, but here we've rearranged it. So you can find the energy of the photon that's going to get released between any given transition, and you can use that number in here to calculate the wavelength of the light. Yeah?
I'm sorry, can you explain what a photon is? It's like a part.
A photon is a piece of light, a particle of light, a packet of energy. Yeah. I remember as a kid being in the backyard, and I don't know what the circumstances were, but one of the neighbor kids was talking about a piece of milk. And that was just the most hysterical thing I had ever heard. How can you have a piece of milk, right? This is kind of the same. How can you have a piece of light? But you can't, because it does act like a particle. So yeah, a photon is a particle of light. Good question. So for hydrogen, those three visible lines that we see correspond to an electron moving from principal quantum level 5 down to 2, from 4 down to 2, or from 3 down to 2. There are many other transitions that can occur. But the ones up here are in the infrared spectrum. It's much smaller energy. And the ones over here are in the ultraviolet region. So there's only 3 for hydrogen that fall in the visible region. And that's true for all elements, that there are some that fall in the visible region, and then there's others that are outside the visible region. They could be measured with instruments, but we can't see them with our eyes. Now this is the kind of question you could see on an exam. Which transition emits light with the shortest wavelength? So let's just think about those principal energy levels, right? So n equals 1 and n equals 2 is higher. And then what did we say about the distance between them? They get closer together. So this would be the wavelength, right? Which of these is higher in energy? The top one. That goes along with just what it looks like to us, right? It looks all bouncy and energetic. This is high energy, so high energy has the short wavelength. So if this is asking us for the shortest wavelength would be the highest energy, so that would be 3 to 2. Questions? Yeah.
Can you repeat what you just said for me?
Yeah, I think I can. So, you were okay with this part? Okay. So, we can identify the smallest and largest energy change, but then if you're talking about frequency or wavelength, you're kind of in the weeds, right? So then you can draw some waves, either, on paper or in the whiteboard in your mind, right? And identify that this is small wavelength and this is long wavelength, okay? And then I ask myself, well, which of these is higher in energy? The top one. Why? Because it looks bouncy, right? Okay, that's not very scientific, but it works, right? It works. So hey, we'll just go with that. So this is the one with more energy. More energy means shorter wavelength. So then if I'm trying to find the shortest wavelength, I'm looking for the one with the largest energy change. Yeah. Yeah. And it's really easy to get lost through there. Determine the wavelength of the light absorbed when an electron in a hydrogen atom makes a transition from an orbital in which n equals 2 to an orbital in which n equals 7. So this is where we're going to use, whoops, passed it. We're going to use this equation. So we've got n equals 2 and n equals 7, and we want wavelength. So delta E is equal to negative 2.18 times 10 to the minus 19 joules times 1 over nf squared minus 1 over ni squared. So we have to identify which of these is the initial level and which is the final level. Well, it says it's going from n equals 2 to n equals 7. So this is n initial and this is n final. The only thing that happens if you get those backwards is the sign is opposite. So negative 2.18 times 10 to the minus 19 times 1 over, the final is 7, so 7 squared, minus 1 over the initial 2 squared. Don't get all fancy and try to find a lowest common denominator and subtract those guys. Your calculator can do it. Yeah?
I think it's 10 to the negative 18.
Negative 18? Thank you. Okay, so negative 2.18 EE minus 18 times, use the parentheses, 1 divided by 7 squared minus 1 divided by 2 squared, close the parentheses, equals. 25.01 times 10 minus 19 joules. But it wants wavelength. Right? The wavelength is equal to Planck's constant divided by blanking. It's HC. HC over E. Let's go back and check. HC over E. So H, look it up, 6.626 times 10 to the minus 34 joule seconds. Speed of light, look it up, 3 times 10 to the 8th meters per second. Dividing by the energy we just calculated. And my calculator is showing me a whole bunch of zeros. These are 6 of them. 1, 2, 6, 397. Joules cancel, seconds cancel, that would be meters. That's a number you should report in scientific notation. Kind of my rule of thumb is if there's more than 3 zeros at the beginning, put it in scientific notation. For some reason, I can see 3 zeros, but when it gets 4 or more, they start to swim, and I have to get my finger out and count them, which makes me feel like a first grader or something. 1, 2, 3, 4. So that's a good time for scientific notation. So 3.97 times 10 to the, and we're going to move this 1, 2, 3, 4, 5, 6, 7. Is that 7 positive or negative? Negative. Because that was a very negative feelings if that was my paycheck. Meters. Any questions?
Nice. Use commas on either side of the decimal point to at least keep track of them easier.
Yeah, it would. But then you get into the fact that in other countries they use commas for periods, decimal points. Yeah, so that's not confusing.